we just talk about one-sided limit. Actually, in the one-sided limit, this is the required fx exists. F is continuous at x. Okay, but we can generalize this to the so-called generalized one-side limit. That is to say, the result remains true if S has generalized one-side limit. Another remark. If F has generalized one-side limit, one-side derivative at x, that is, we denote by d plus f x, which is the limit of h goes to 0, fx plus h minus fx plus over h, and d minus fx is the limit h fx minus h minus fx left limit. So in this we require that fx plus and minus exist. That is, f has one-side limits at the point x and also has one-side derivative at the point x. The one-side derivative is defined using these two limits. Okay, then exactly the same proof. Exactly the same proof here. The only difference is that here fx is not fx, is the one-side limit of f at x. So exactly the same proof, we will see that f also satisfies whole continuum of order 1, and thus the Fourier series converge to the mean value of the one-side limit at x. That is half of a0 plus k from 1, ak cosine kx plus bk sine kx is the mean value of the one-side limits of f at x. Okay. Now we consider some example. We consider the function fx is x squared 1 minus pi. So f is such a function. Minus pi. Okay, but f is a periodic function, so it extends to the whole real axis. So this is f. The blue part is the expression given by this. Okay, f is such a function. So f is derivative, differentiable. Differentiable at points. So here is pi, minus pi, here is pi. So here's 2 pi, here is 3 pi. F is this differentiable for x not equal to 2k plus 1 pi. K is integer. Okay. Because at such point, for example here, For example, a point like this, the left derivative does not equal to the right derivative. Okay, so f could not be differentiable at pi and at minus pi, and so on. But it is differentiable at point not integer multiple of pi, and also even it is also differentiable at even multiple of pi. For example, 0 and 2 pi and minus 2 pi. Okay, f is differentiable at those points, and f has one side derivative at every point. Okay, for those points where f is differentiable, the one-sided derivative of course exists. For those points where f is not differentiable, that is all the multiple of pi, for example, minus pi and pi, 3 pi, 5 pi, f is not differentiable, but it has one-side derivative. It is easy to see. It has one-side derivative. For example, at minus pi, the right derivative of minus pi is minus 2 pi. Okay, the limit of the derivative. So you can see that the left and right derivative of f at minus pi is minus 2 pi, as you can check. Okay, it is easy calculus. So this f satisfies our condition that f is has one-sided derivative. Therefore, the Fourier series of f converge everywhere, and the sum of the Fourier series is injected in f. Okay, so we obtain that fx equal the Fourier series. To determine the Fourier series of f, we compute the coefficient a0. A0 is 1 over pi minus pi x squared dx, which is 2 over 3 pi squared, and the ak is 1 over pi minus pi x squared cosine kx dx, and you can compute this integral and find that it is minus 1k 4 over k squared. Similarly, bk is 0. Okay, why bk is 0? Because f is even function. So bk is minus pi fx sine kx dx. So f is even, sine kx is odd. So this integral over minus pi to pi for this odd function must be 0. So the Fourier series of f equal fx everywhere. So maybe I will write in this way. The Fourier series of f is exactly half of a0 plus sum of k from 1 ak cosine kx. That is half of a0, that is 1 pi square over 3, because a0 is 2 over 3 pi square. Therefore, half of a0 is pi square over 3. And ak is minus 1k over 4, so plus k equal to 0 minus k 4 over k square, then cosine kx. So this is the Fourier series of f. But because f satisfies our previous condition, f has one-sided derivative everywhere. So for every x, f the Fourier series of f converge to f. That is, fx is precisely the sum of its Fourier series. So the symbol, this relation, can be replaced by equality. So we obtain this equality. Fx equal pi squared over 3 plus the sum of cosine kx, where x is for, this is true for arbitrary x real number. Okay. So we can take a particular x. We take x to be pi. Take x to be pi. Then the left hand side is f pi. F pi is pi squared equal 3 pi squared plus the 4 in the series can be moved outside the summation, plus 4 sigma k from 0 minus k squared cosine k pi. Cosine k pi is minus 1k. Okay, cosine k pi, when k is even, it is 1. When k is odd, it is minus 1. Therefore, it is minus 1k. So the left hand side become 3 over pi squared plus 4 summation 1 over k squared, k from 1. So from this we can solve for the sum of 1 over k squared. We conclude that sigma 1 over k squared, k from 1. You move the pi squared over 3 to the left, you obtain the 2 pi squared over 3. Then divided the 4, you obtain the sum of 1 over k squared, that is pi squared over 6. Therefore, using Fourier series, we have an amazing result. 1 over k squared, summing up, you obtain the pi squared over 6. So the left hand side is only related to natural numbers, but the right hand side there is very interesting number, pi. Okay. So we consider the next example. Fx is x 0 to 2 pi. So we draw the picture of this f. 0 to 2 pi. F is x. So and at 0 it is not defined. So it is the graph of f is this. And then you extend this periodically. This is 2 pi. This is 4 pi. This is 0. And also you have minus 2 pi. F is defined in this way. Okay. So you see that f has one-sided derivative. F has generalized one-side derivative. For example, at 0, we consider the generalized left derivative at 0. That is the limit of h goes to 0. F 0 plus h is positive, go to 0, minus f 0 plus divided by h. So f 0 plus h is positive. So this is the limit of h goes to 0. This is h. F 0 plus h is h. Okay. And the right limit of f at 0, the left limit of f at 0 from this picture, obviously the limit is 0. Okay, the left limit of f(0) is 0. So minus 0 divided by h, and the limit is 1. So the generalized right derivative at 0 is 1. Similarly, you compute the left derivative at 0. That is the limit h goes to 0. f 0 minus h minus f 0 one side limit. Okay, now what's this? f 0 minus h is minus h, right? So this is limit h goes to 0. Because h is positive, minus h is negative, so minus h is here. So the value of f at this point is is this point. And the right limit, what's this? This is 1. 2 pi. This is 2 pi. So the left limit at 0 is here. From the picture, you see that it's here. So this quotient is the slope of this line. So the slope is 1. So the slope is 1, right? Although if I want, I can write the equation of this segment. I can write the equation of this segment and give you the value of f(0) minus h. But I don't need to do this because I observe that this is the slope of this segment. It is 1. So I don't want to make this stupid computation. I know that it is 1. So both the right derivative and the left derivative at 0 is 1. Okay. Similarly, you can compute the generalized one-side derivative at other points. You will see that all the one-side derivative exist. Okay. So by the previous discussion, we know that Fourier series of f converge everywhere at x. Converge to not fx anymore. Converge to the mean value of the one side limit of f at x. Okay. Converge to the one side limit, mean value of the one side limit at x. Now we can compute the Fourier coefficient of this function. So a0 is 1 over pi 0 to 2 pi. Our previous computation is minus pi to pi, but it is the same for 0 to pi for other kind of interval, as long as the interval is of range 2 pi, because we are considering 2 pi periodic functions. Okay, so fx. And this can easily be computed because in this case fx is precisely x. So the result is 2 pi. And ak is 1 over pi 0 to pi x cosine kx dx. You will see this is 0. And the bk is 1 over pi 0 to pi x sine kx dx. And this is easy to compute. It is minus 2 over k. Okay. So the Fourier series is that the Fourier series of fx a0 is 2 pi, but half of A0, that is pi, minus the sum of k from 1. bk is minus 2 over k, then sine k pi, kx. So this sum, this the right hand side is the Fourier series. It converges everywhere. The limit is what? The mean limit is the mean value of the one side limit at x. So at x equal to 0, the mean value at 0, you see, the mean value at 0, because the left limit is 2 pi, the right limit is pi. Okay, you see, when x goes to 0 from the left, fx goes to 2 pi, and when fx goes to 0 from the right, fx goes to 0. So the mean value is pi here. Okay, so the sum of this Fourier series is pi when x equal to 0. And when x is taken from 0 to 2 pi, when x is in the interval 0 to 2 pi, fx is continuous. Okay, in the open interval 0 to 2 pi, fx is continuous. So the left limit and the right limit at any point x in this interval is the value of f at that point. But the value at x is precisely x, because our fx is fx equal to x in this interval. So we see that when x belongs to this open interval, the Fourier series, the sum of the Fourier series is x itself. And how about x equal to 2 pi? When x equal to 2 pi, the function does not continuous. It's not continuous at 2 pi, but the one side limit exists, and the Fourier series converges to the mean value of the one side limit. Now at 2 pi, the left limit is pi. The left limit is 2 pi. The right limit is 0. So the mean value is pi. So when x equal to 2 pi, the result is still pi. Okay, so this is the result. Now we can take x to be some interesting number to obtain some sum of the some numerical series. For example, you can substituting x equal pi over 2 to this series and obtain sum of a numerical series. Okay, I will not do this here.